Okay, in this lecture, we're going to talk about what's called a mass spring damper system. Let's first draw what the system looks like. We have a wall, we have a mass sitting on a frictionless floor. Okay, frictionless surface. And this is a rigid wall. And this mass is connected to the wall by a spring with spring constant K. And we have another object connecting the mass to the wall called a damper, which is drawn like this. Okay, so I'll talk about the damper in a minute, what that means and so on. The mass is M, spring stiffness is K, and what's called the damping coefficient is C, let's say. And the spring also has a rest length or a stress-free length. Spring rest length, which is called the force-free length, stress-free length, whatever. Sometimes called the unstretched length. Okay, all the same thing. Let's call it L naught, okay? Like we said, we'll talk about what the damping coefficient is and what the damper is in a minute. But these are the main notation. And then let's denote the total length from the wall as L. And then let's denote, let's say the spring length, rest length is L naught. And if you start measuring from L naught, that's equal to X. Okay, so just introducing some notation here. That's X, okay? X is distance measured from unstretched spring position in this particular case. Okay, so that's the system that we are going to consider. Before we can write equations of motion, we know what springs are, we know what a mass is. Some of you may know what a damper is as well, but let's just write down what a damper is. Okay, so a damper is represented by an object like this. Okay, so if this thing is connected to a wall, and this point moves at, let's say, velocity v, then the Freebody diagram of the damper is the following. So it's a massless object. The Freebody diagram is like this, where there's a force F here, there's a force here, F here, and the force F is basically equal to minus CV, okay? Where V is the velocity of point P. This is when the damper is connected to a rigid wall. If you have the damper connected to 2 points, both of which can move, so let's say you have a force F like this, and you have this point is at a distance x1, and this point is at a distance x2. From some fixed wall, let's say, then F equals basically the relative velocity of this point and this point, minus C x2 minus x1. Okay, so let's unpack these things. So what is the damper? If you're trying to move this point, or in this case this mass, right side by a velocity v, it produces a force that is equal to, well, actually this force should be equal to plus CV. This force equals this thing. Okay. Okay, so it produces a force. It requires a force to pull this point at a velocity v. It requires a force that is proportional to the velocity v. Okay, so it's as if this point is being pulled back by the damper with a force CV, where it's a force that is proportional to velocity. So it's basically the same as drag. Same as what would we call linear drag. Okay, so the reason why we draw it like this is because this is a way to actually construct a damper. You have a piston with some air inside, and then you have a hole on the piston, and if you try to pull this out, air will try to slowly escape. The only way you can pull this out is to have the air escape, and it turns out that work needed to let the air escape or increase the volume of this area is roughly proportional to C times V, proportional to the velocity with which you're pulling this. Okay, so sorry, I should have written this as x1, x2 dot and x1 dot. It's because that's velocity. Okay, I meant to say velocity here, not x2 minus x1, because that would just mean a spring. This is x2 dot minus x1 dot. Okay, so now we know what dampers are. You can find real life versions of dampers in your doors. Doors have essentially an object like this, which self-closing doors, where you have a spring which produces the force that pulls the door back, and then a damper essentially makes sure that the spring doesn't pull the door too fast. It slows it down in a manner that the motion back to door closed, let's say, is slow enough. So it essentially tries to oppose the spring, oppose the velocity of the door. So example, dampers in door closing mechanisms. Okay, so that's what a damper is. Okay, now let's put everything together in terms of a free body diagram here. So let's draw a picture. We have a mass M. Nothing happens in the vertical direction. There's normal reaction N, gravity mg. And then in the horizontal direction, we have kx in this direction, and then cx dot, namely the velocity in this direction, right? So this is actually the free body diagram for the mass. If you want to draw a free body diagram for the spring itself, it's going to look like this. It's going to look like kx like this, kx like this, and then for the damper, it's going to look like cx dot, cx dot. Okay, so these are the forces on the spring and the damper. Notice that this is what we had when we had something like this. Okay, and then because you you have Cx dot in this direction. On the mass, it's Cx dot in the exact opposite direction. Okay, so that's how you draw free body diagrams for the springs and the dampers and the mass. Okay, now that we have that settled, we can now write equations of motion. We have sum of forces in the horizontal direction, let's say, equals mass times acceleration in the horizontal direction. So what is the sum of forces in the horizontal direction? Specifically in the x direction, it's minus kx minus cx dot, because they are in the leftward direction, equals m times acceleration a is basically L double dot, where L is this whole length of the spring, or it's equal to x double dot, because x double dot is just L double dot, because x is just L minus L naught, and if you differentiate L minus L naught twice, L naught will drop off because L naught is just a constant, okay? Equals m x double dot. Because L equals L naught plus x implies L double dot equals x double dot, as L naught equals constant. Okay, so this is the key equation, and we can rearrange the equation in this manner. And this equation is the equation for a mass spring damper. This is called an equation of motion. For a mass spring damper system. And it's what would be called a second order linear ordinary differential equation. So if you took your ODE class, differential equations class, it's a second order linear ordinary differential equation. And the next 3 lectures, we will essentially use what you learned, or essentially go over what you learned in your differential equations class to try to solve this. So you do not need the prerequisite necessarily of the differential equations class to understand what we do in the next few lectures, but because we will repeat it. But essentially what we're going to do is essentially solve this equation for x of t, x as a function of time, in the next few lectures to find the motion that a mass with a spring and a damper will describe. So the idea is that we have this mass connected to the wall with a spring and a damper. You pull it and let go. What happens to the mass? It will oscillate. And if there was no damping, the oscillations will persist forever because there's no damping and there's no friction. But if there is damping, what will happen is that the mass may oscillate and then the oscillations will die down, or sometimes the mass might come to a stop without oscillation. You pull it, let go, and then it slowly comes to rest. Both these kinds of motions are possible, but essentially the next few lectures will talk about those possibilities. And that's it. The next few lectures are going to be an expansion of this equation.